Hello, hello, hello. Having conversation with Gemini, revisiting some of the concepts. So my question is, what are the most important hyperparameters of a neural network, especially for large language models? So let's see what we got here.
Networks, NNs, with a special focus on large language models, LLMs. Keeping in mind today's date, April 9th, 2025, reflects current common practices. Hyperparameters are settings configured before the training process begins, as opposed to parameters, like weights and biases, which are learned during training. Tuning hyperparameters is crucial for model performance, convergence speed, and resource utilization. Most important hyperparameters for general neural networks. 1. Learning rate, ETA or alpha. As discussed previously, this is often considered the single most important hyperparameter. It dictates the step size during gradient descent, requires careful tuning, often using schedules or adaptive optimizers. Related, learning rate schedule, e.g., step decay, cosine annealing, warm-up steps, gradually increasing LR at the start. 2. Optimizer, the algorithm used to update the weights based on gradients. Common choices,
So
atom, atom W, RMS prop, SGD with momentum. Importance, affects convergence speed, stability, and potentially the quality of the final minimum found. Atom/atom W are very popular defaults currently. 3. Batch size, the number of training examples used in one iteration, forward/backward pass, to estimate the gradient. Impact, affects gradient noise, smaller batch equals noisier, training speed, hardware utilization, memory consumption, and can influence generalization. Sometimes smaller batches generalize better, sometimes larger ones are needed for stability. 4. Network architecture. These define the model's structure and capacity. Number of layers, depth. More layers allow learning more complex hierarchical features, but increase computational cost and risk of vanishing/exploding gradients. Number of units/neurons per layer. Width. Wider layers increase capacity, but also computational cost and overfitting risk. Type of layers. Dense, convolutional, recurrent, attention, etc. Fundamentally chosen based on the task and data type. Activation function. ReLU, GeLU, introduces nonlinearity.
So types of layer is interesting. Dense layer, convolutional layer, recurrent layer, attention layer. Okay. So these are the four most popular right now.
Affects gradient flow and training dynamics. ReLU and its variants, like GeLU, Swish, are common in deep networks. 5. Regularization techniques, methods to prevent overfitting. Weight decay, L2, regularization, penalizes large weights. The strength of the decay is the hyperparameter, very common. Dropout rate, the probability of randomly setting neuron activations to 0 during training, helps prevent co-adaptation of neurons. The rate is the hyperparameter. Early stopping, monitor validation performance and stop training when it ceases to improve. Patience, how many epochs to wait, is a key hyperparameter here. 6. Number of training epochs, how many times the entire training dataset is passed through the network. Too few leads to underfitting, too many leads to overfitting, if not using early stopping. 7. Weight initialization scheme, method used to set initial weights, e.g. He, Xavier, Glorot, can significantly impact initial training stability and convergence speed. Hyperparameters especially crucial for LLMs.
Okay, weight initialization scheme is also interesting. He, Javier, and Glorot. I have never looked at them. Okay, let's continue to LLM.
Transformer-based. LLMs are typically massive transformer models, making certain hyperparameters even more critical due to scale and architecture specifics. 1. Model dimension/architecture, paramount. These define the scale and capability, directly impacting performance and computational cost. Number of transformer layers, blocks, depth, e.g. 12, 24, 48, 96. Determines the model's ability to capture complex relationships. Hidden dimension size, D_model. The main width of the model. Embedding size, input/output of attention/FFN layers, e.g. 768, 1024, 2048, 5120. Number of attention heads, how many different perspectives the self-attention mechanism uses in parallel. Must divide D_model, e.g. 8, 12, 16. Feed-forward network hidden size, D underscore FFN, the size of the inner layer and the position-wise feed-forward networks. Often 4 asterisk D underscore model dot vocabulary size, the number of unique tokens the model knows. Impacts embedding table size dot maximum sequence length slash context window, the maximum number of tokens the model can process simultaneously. Crucial for capturing long-range dependencies, but quadratically increases computation slash memory in standard attention. E.g., 512, 1024, 2048, 4096, 8192, 32K plus. 2. Learning rate and schedule. Still absolutely vital. LLMs often use very specific schedules. Peak learning rate. The
now
maximum.
we are again in learning rate. So we set peak learning rate as a hyperparameter, warm-up steps ratio, number of initial stays, where the learning rate increases linearly or polynomially to the peak value, essential for stabilizing training early on. Okay, that's good. For large models, learning rate usually needs to be relatively small. Okay, fair enough. Decay schedule. Cosine decay is extremely common for LLM after the warm-up phase. Okay, fair enough. Okay, let's continue.
Learning rate reached, often after warm-up. Usually needs to be relatively small for large models, e.g., 1E5 to 3E4. Warm-up steps, ratio. Number of initial steps where the LR increases linearly or polynomially to the peak value. Essential for stabilizing training early on. Decay, schedule. Cosine decay is extremely common for LLMs after the warm-up phase. 3. Batch size, often measured in tokens. Due to varying sequence lengths, batch size is often defined as the total number of tokens processed per gradient update, e.g., batch underscore size asterisk sequence underscore length. Impact. Larger effective batch sizes, e.g., 2M, 4M tokens, are often needed for stable training of huge models, requiring massive distributed training setups, data parallelism. 4. Optimizer settings. Optimizer choice. Atom W is the dominant choice for LLMs currently. Atom betas, beta 1, beta 2, and epsilon. Epsilon, while often left at defaults, beta 1 equals 0.9, beta 2 equals 0.999 or slightly lower like 0.95/0.98 for large models, epsilon equals 1E-8 or 1E6. They can sometimes be tuned. 5. Regularization, dropout rate, applied at various points, attention, embeddings, FFN. Often around 0.1, but can be tuned. Weight decay, crucial for preventing overfitting in massive models. Typical values might be 0.01 or 0.1. 6. Gradient clipping, threshold value used to clip gradients if their norm exceeds this value. Prevents exploding gradients, essential for stable LLM training. A common value is 1.07. Positional encoding. While more an architectural choice, the type, e.g., learned
So this is an interesting trend where gradient is clipped at 1.0, the highest value, the threshold that it can never be crossed. Yeah, fair enough.
Lute fixed sinusoidal relative like rope, rotary positional embedding, is fundamental and decided before training. Rope is very popular in current performant LLMs. In essence, for LLMs, the architectural dimensions, layers, D underscore model, heads, context underscore length, define the model's potential, while learning rate with schedule, batch size, tokens, optimizer, Atom W, regularization, dropout, weight decay, and gradient clipping are the key knobs turned during training to realize the potential effectively and stably, often requiring vast computational resources.
Okay. Let's end the conversation. Okay. Peace.